Why don't planes bump into each other? The easy answer is the Kalman-Schwarz filter, but that doesn't really mean anything on its own. So instead, I'm going to make this little series where I explore basically the history of big things bumping into each other and what we do now to make sure that it doesn't happen and why that's going to be even more important as we go forward into the future. So this series is going to be called Why Don't Planes Bump Into Each Other? Just because that is sort of the unifying theory here, but we're actually going to start with bumping into something intentionally. I'm talking about the moon. Before the 60s and 70s, planes did bump into each other, and so did boats and a bunch of other things, and I mean, some of those still do. But the math behind bumping into things wasn't really thought about a lot because nobody was really that concerned about it. You would just come up with rules and steer away from each other. But when it comes to bumping into the moon, which is really what landing on the moon needs to be, you need to start thinking about the way that a lot of different things move. When you first look at this, you see, okay, we've got the Earth, we've got the moon, I want to go from one to the other, bingo, bango, bongo, we're done. Except this is really, really far. And the moon is also moving really fast. So the moon is moving around, so you have to time this flight such that you shoot off at a time that the moon comes and meets you at the same spot. Except it gets more complex than that because you can't just sort of shoot radially off the Earth. I mean, you could, but that would actually take a lot of energy. You see, the way that things fly anywhere, actually, if you just throw a rock in the air, you'll see that it sort of like curves back down. So rather than trying to throw yourself straight up, in which case you'll just curve right back down, that will require an absolutely bonkers amount of energy to sort of end that arc right at the top. Instead, if you throw yourself forward, you sort of arc like this. And if you throw yourself forward far enough, you will end up missing, basically, when you fall back down. Now, this math starts to get a lot more complex right away because, you know, you are accelerating the entire time you're doing this, so the shape of this arc is changing. What even is speed starts to become a question because we're used to sort of just measuring against the ground, but that starts to get weird here where at the top of the arc you're no longer actually moving relative to the ground, but you're also moving ridiculously quickly. When do you go and sort of like throw yourself again from here to start to create an orbit? And actually in the Apollo missions they did the entire relatively circular orbit in one burn, which is pretty bonkers. Anyway, also while this is happening, the moon moves around ridiculously quickly, but the Earth is also moving. Like the time it took them to fly to the moon and back was over a week, which means that the Earth in that time traveled, 1/50th of the way around the sun. So you have all of these moving parts and you need to be able to, figure out how they all go. So once you've done all this trig though, you should be able to just pull out your handy dandy pocket calculator and get number crunching. There's some trig functions up in there and you can pretty much bang these things out. Except there was another problem with this. Back when Lance Armstrong and Buzz Lightyear were trying to fly to the moon, they didn't have pocket calculators. Those weren't invented for another 4 years. Instead, they had to do the whole thing with ye old slide rule, and I actually have one here. This is my grandfather's old slide rule. I think that he jokingly gave it to me when I went to university to do engineering. And I actually did go ahead and learn how to use it. So this is a slide rule that I think is from 1958 based on Googling some serial numbers. I think it would have sold for $3, which is about $25, $30 today, which seems reasonable. And the way that a slide rule works is actually very interesting, and it's particularly interesting to me as a computer engineer, because computer engineers love taking, beautiful, round, curvy numbers and turning them into discrete things, right? And most other types of engineering, including our awkward brothers, the electrical engineers, they love having sine waves and, weird, interesting, curvy things. And computer engineers like to just round everything to one and do what's called discrete math, basically. And some of the most elegant math out there is taking these nonlinear equations and making them linear such that a computer could calculate them. And that's what the Kalman filter does. But what's so interesting to me about a slide rule is that it actually does the exact opposite of that. What it does is it takes math that most people would look at and think, this is pretty discrete. This is a pretty linear problem. It's an integer multiplied by another integer. And the way that a slide rule actually approaches this is by taking the log of both sides of these and then taking the anti-log of the answer. Because actually another way to do this math is if you do the natural logarithm of 2 plus the natural logarithm of 3 is equal to the natural logarithm of the answer, whatever that is. And if you go and take the anti-log of this, you can figure out what the number is just by doing linear addition. So when you actually look at the slide rule, you will notice that pretty much everything on it is logarithmic. The space between 1 and 10 is exactly half 10 to 100. And basically by using this ruler is actually a pretty deluxe edition. It's the C model. It has 9 different tracks on it. So you see some on this side, and actually there's a few bonus ones on the back here. I will actually go and sort of make videos about how to use each of these different tracks to use different pieces of math, but it's actually incredible to me how much you can calculate just with this slide rule like this. When you look on the back, it's got some cheat sheets on how to use the scales, and it also goes and tells you about specific points that have been marked on it for all kinds of different things. So you can't just do addition and multiplication with this. You can do, the opposites of those, subtraction and division and, square roots and things like that. There's actually nifty shortcuts for, but you can even do pretty complex trigonometry. It's got conversions for other things. A lot of weird esoteric units are on here. Like if you want to know how to convert between kilowatts and BTUs per hour, or horsepower to kilowatts, or various things like that, cubic foot of water to weight in pounds. That's all built into this, basically. All of your sort of tangent, sine, cosine, all of those things are built in there. It even has a way to quickly convert from radians to degrees, and not just degrees, but also minutes and seconds. So it walks you through basically how to multiply a radian by 200,006, oh boy, I can't even read the number of seconds. Today we sort of use degrees as a decimal number with 50.5 or something. We would never say degrees, minutes, and seconds of a circle, despite the fact that we're pretty accustomed to using 360 degrees in a circle. I always thought that was kind of funny that we didn't divide the circle into 100 chunks with 100 subdivisions or something. Anyway, that's where that comes from, and this ruler can help you do that math as well. And it also has a few other, points marked on it for, pi and Euler's constant and C. And on the back, it's got a little bit of information about those things. And as you use pi and Euler's number all of the time in most of the math I'm accustomed to, but I'm not used to C. C is usually the speed of light or the charge of a constant particle or something. I'm not used to whatever this C is, which is roughly 1.128 according to the back of this ruler. It looks like it might have something to do with the volume of a cylinder. I was Googling around and couldn't really find a good answer. It is equal to the square root of 4 divided by pi, which is kind of a bizarre, like a circle of radius 2 or something, maybe. You can figure out the area of a circle or the volume of a cylinder using that, perhaps. The website that I did find that was talking about it being used for gauge, American Standard Gauge, how wires relate to things. There is math that does involve a square root of 4 and a pi, but they're not arranged in the way that gives you 1.2. So I can't really figure out what the C is for and why it would be one of the only 3 constants that would be included on this. So if anybody's more familiar with actually using these and what the C was for, that would be helpful. But yeah, let's just go ahead and try to do 2 times 3. So to do multiplication and a lot of the simpler operations on this, you use the C and D scales basically here. So all you have to do is take the 1 on the C scale and slide it over. That's why it's called the slide rule, such that it lines up with the 2. We then take the little window here and we slide that over to the next one on the, bottom. Two times 3. My 2 times 3 isn't working out. Right, so earlier when I mentioned that it doesn't help you with decimals, that's actually what confused me here. So this 2 is actually 1.2. That's why we've got 1 twice in a row here. Actually, I needed to slide it all the way over to this 2. And now if it's slid over to this 2, and then we slide the window, so here, I'll do it again. We slide the 1 not to 1.2, which, I mean, would work if I wanted to do 1.2, but I want to do 2 times 3. I slide it all the way over to this 2. So now we've got the 1 and the 2 are, well, almost lined up now. And then we slide the window over to the 3, and we can see that 2 times 3 is 6. And you can do this for more complex numbers as well. So like if I wanted to do, I don't know, 1.5 times 3. There we go, and we can see that that is, well, we can't actually see very easily what it is because the window happens to be covering it up, but it's between 4 and 5, halfway there, so we can see that that is 4.5, which I think is just a really nifty way to do math. So I'm going to make another video where I explore all of the different ways that you can do math with this, so that will be the next one. Anyway, have a beautiful day. 1, 2. 2 times 3 should give me 6, shouldn't it? Problem. Here we go.